Hello and welcome to CIC Start Online webinar here at Glasgow Caledonian University. My name is Branka Dimitrijević and I will moderate today's event. Our events disseminate outcomes of feasibility studies and academic consultancies undertaken through our project. It is a joint project of 7 Scottish universities and it supports collaboration between academia and Scottish small to medium-sized enterprises. This project focuses on sustainable building design and refurbishment. The project is funded by European Regional Development Fund and Scottish Government CIC program. This is a live event, so if there is a fire alarm, we will have to stop and we will continue later. And if you can join us, that is fine, but if not, then you can watch a video recording of this event tomorrow or in a few days. During this event, online viewers will be able to use chat facility, and you can start using chat facility at any time during the event to ask questions. But the question and answer session will start at around 1:30 o'clock. We plan to finish around 2 o'clock. So today's seminar title is Implications of Installation of Solar Photovoltaics on Properties of Fairfield Housing Cooperative. This is a study that was undertaken by the Glasgow School of Art and Edinburgh Napier University in collaboration with Fairfield Housing Cooperative. And our speakers today are Anila Ahmad of Fairfield Housing Cooperative, Dr. Masa Noguchi of Glasgow School of Art, and Professor Tariq Muneer of Edinburgh Napier University. I would kindly now ask Anila Ahmad to start with her presentation.
Thank you, Branka. Good afternoon, everybody. Thanks for joining us in this Kickstart webinar, whether you're joining us in person today or whether you're watching through the live web broadcast. I'd like to thank, first of all, the academic team. I'd like to thank Dr. Noguchi and Professor Muneer and Branka for the smooth collaboration of this online webinar and the support they provided throughout the project. As Branka introduced me, I'm Anila Ahmad and I work for Fairfield Housing Cooperative in Perth. I'm a corporate governance officer, and whilst I don't boast to have much technical expertise or specialist knowledge about PVs, I'm glad to say that I have learned quite a lot through working closely with the academic team. I'm going to give you an introduction to Fairfield Housing Cooperative, and I'm going to set the context by explaining to you the reasons why we were interested in investing in PVs. I explained to you the reasons why we thought we would benefit from an academic study, and obviously the outcomes of the feasibility study itself. My colleague Masa will then join you and explain to you a bit more about the analysis which led to the conclusions of the study. Okay, so Fairfield Housing Cooperative is a registered social landlord in the now city of Perth. We provide quality and maintained and affordable houses to those in genuine need. We have over 25 years of experience in the industry and we have just over 450 homes under management. This makes us one of the largest housing providers in the city of Perth. After the successful transformation of Fairfield itself, we're working quite closely with a local partner, which is Caledonia Housing Association, to regenerate the area of Muirton Park in Perth. This is a multi-million-pound project and it has seen a reversal in the decline of the fortunes of many of the people that live in that area. It's now a more thriving area and it was once quite a deprived area, so we're quite proud of that achievement. Regeneration has always been at the centre of Fairfield's work since it began. Most notably, we were the UK pioneer, the first in the UK to invest in low allergy housing. We developed 14 homes in one of our areas called Toll House Gardens, and these are all low allergy homes. Now, these homes were designed to avoid the use of building related allergens which cause allergies amongst people, and they're also designed to minimise the conditions in which those allergens would flourish. In a separate project, we also developed a small number of homes using the Kingspan Tech panel system. These are timber panels which are highly energy efficient. They are constructed off-site and they They have integrated insulation into them. They're very heavily insulated, and they create very energy efficient homes, and they have a relatively short construction period on site. So these were two very successful investments that we've made. More recently, however, we've been looking at installing PV to our properties, so that's been our recent focus. Okay, so why were we interested in solar panels at all? The primary reason we were interested in investing in PV technology, solar PV just stands for photovoltaic panels for those that aren't aware. The reason we were interested in investing in solar photovoltaic panels was to tackle fuel poverty. Now, fuel poverty is a major issue for many people in Scotland. For those of you that aren't aware, fuel poverty can be defined as any household which has to spend more than 10% of the household's income on its energy costs can be defined as being in fuel poverty. Scottish Government figures indicate that in 2002, 13% of Scottish homes suffered fuel poverty. In 2009, figures showed that there was a huge rise in this, and 33% of homes suffered fuel poverty. Now that's an increase of 154% in only 7 years. Initial conversations with local and national PV companies indicated that if we were to install PV panels to our tenement properties, the tenants would save on average £100 a year. That was quite an interesting stat for us, the reason being most of our properties are either 4 in a block or 6 in a block properties. A secondary reason we were interested in the feed-in tariff was because of the Scottish Government's, at that time, very generous feed-in tariffs. At the time of the feasibility study, the rates we were referring to were 43.3 pence per kilowatt hour plus an export tariff of 3.1 pence. Now, for those of you that don't know, in the context of solar panels, the feed-in tariff refers to a payment which is made per kilowatt hour of electricity generated through the panels. So in this context, if PV panels are applied to a house, they generate power. For each unit that is generated, you would get a payment of 43.3 pence. For any power that's generated but not used and therefore exported back to the grid, you would receive an additional payment of 3.1 pence. And at the time of the study, this was guaranteed for 25 years. So according to these figures, we expected to have a payback period of around 10 years or less than 10 years. Another reason we were interested in investing in PV technology was to contribute towards Scottish Government targets. The targets in question were to reduce carbon emissions by 80% by the year 2050. The Scottish Government also hopes that by 2020, 100% of Scottish homes, so 100% of the electricity consumed by Scottish homes will come from a renewable resource. And finally, we're also working towards the fuel poverty target of 2016, where we aim to end fuel poverty amongst Scottish homes as far as possible by 2016. For those of you that aren't familiar with how the feed-in tariff works, this diagram explains to you in very basic terms how it works. So as explained earlier, the panels will convert solar radiation into electricity. For each unit of power that is used by the house, you would get a payment of 43.3 pence. For each unit that is generated but not used and exported back to the grid, you would receive an additional payment of 3.1 pence. So you've got the generation tariff and also the export tariff. And at times where the power through panels is not sufficient, it would be supplemented through power from the grid. So you would import power from the grid just to supplement the power where it's not sufficient. Okay, now before Fairfield applied for a feasibility study, we did receive quotes and desktop surveys from local PV companies and national PV companies. However, we felt that we would benefit from an independent advice, unbiased opinion on things like what energy outputs we can expect, the true savings we can expect, and a true projection of what the payback period would be. More specifically, we were interested in finding out the long-term and short-term impacts of installing PV panels on our properties in terms of the physical, economical, environmental and social issues attached to installation. Obviously, one of the main benefits to us would be to reduce our carbon emissions and to make our properties more energy efficient. In terms of the social impact we were concerned about, we were worried, we wanted to address issues such as what the real benefit would be to our tenants, what real savings would they make, and obviously if you are applying PV panels to certain properties and those tenants are benefiting from the free power and then making savings, then do you couple that with an increase in the rent? So these are some of the issues we have to think about. And also we have a lot of 4 in a block and 6 in a block properties. Initial conversations indicated that in the case of a 4 in a block or 6 in a block, you may not be able to supply power to everyone in the block, so you may only be able to supply power to perhaps 2 in the block or 3 in the block. So how do you reconcile these issues? How do you make it fair for everyone? So these were some of the questions that were bothering us, and obviously we wanted to go for an academic study just to overcome these hurdles. Okay, so as such, an academic feasibility study went ahead in October of last year. This consisted of 2 site surveys, and a final report was handed over to Fairfield Housing at the end of October. Now, we were advised by the academic team and our preferred PV contractor that it would make more economic sense, given the cost of inverters and the cost of panels, that we invest in a phased project. So this would mean that we start off with 1 pilot installation rather than rolling out to many properties to start off with. So in the first site visit, we identified 3 properties that were potentially suitable for solar panels. But a second, more in-depth survey reveals that only 1 property showed the ideal features, showed the optimal conditions for PV panels. This property we will refer to as the green building. They were all of different colours, so this one was the green building. The advice we received was to proceed with a pilot on the green building purely as a commercial venture. This was because of the high feed-in tariff and because it made more economic sense to do so. And obviously we'd be able to take advantage of the 43.3 pence and the 3.1 pence export tariff. The project that we went ahead with then was to install 42 panels, including 3 inverters on a 10 kilowatt system. This was a recommendation at the time. The projections estimated that there would be a 7 to 10 year payback period for this. However, shortly after we received this report and we digested it and we started to make plans to install panels, the government changed its mind on this. So the government announced that it would have the feed-in tariff, which meant effectively that the payback period of 7 to 10 years would double. So this was a spanner in the works, to say the least. So at that time, our preferred contractor, was unable to go ahead and fit the solar panels by the new deadline of the 12th of December 2011. Obviously, after this date, you would only get half the feed-in tariff. Because we weren't able to install it by this date, at the time we postponed the plans altogether. We didn't go ahead with any installation. However, in another twist of fate, the government re-announced in February of this year that it would extend the date for the full feed-in tariff to the 3rd of March. This was a very welcome decision by us, and it opened up a window of opportunity, and it meant we could reconsider installing PV panels, and it's something we did consider very seriously. As such, we did go ahead with an office installation, which was fitted at the end of February this year. We went ahead with a system which was just under 4 kilowatts. This was installed in our office. It comprises of 16 premium panels and 1 inverter. This was a very proud moment of us. It was the first time we'd ever installed PV panels, and I believe we might be one of the first, if not the first, to install PV panels in the city of Perth, in the city centre of Perth. So this was a very proud moment for us. It turned out to be a very time-effective and cost-effective exercise. The panels were put up within a matter of days, and we managed to get the installation up and running, installed and registered by the deadline of the 3rd of March. This meant that we would benefit from the full feed-in tariff of 43.3 pence, which was guaranteed for 25 years. This made a lot of economic sense for us, and it was a value for money project because economically we're saving money, Through energy costs, we're getting free electricity. We're also getting a quarterly income stream from the feed-in tariff. And obviously at the same time, we're reducing our CO2 impact, and our office itself is now a lot more energy efficient. So it was a very proud moment for us, and it came about through the hard work of the academic team, and as a result of that. At the moment, I have to say, we don't have any solid plans to install PV on any further properties. However, it is something we would consider very seriously doing so in the future when we develop more properties. So that's all from me. I will now pass you on to my colleague Masa, who will explain to you a bit more about the analysis which led to the recommendations.
Well, thank you very much for introductions. And Anila presentation obviously give you some insight and overall picture of the project itself, I guess. My sections is, well, it's not really skyrocket one. It's a kind of soft aspect of architectural considerations for the installation of the PV. And these procedures are very often ignored in a practice, but in reality, it's extremely important procedures to identify exactly where the PV should be installed. Okay, so some shading assessment has been conducted, and I'm going to explain the outcomes later stage. Okay. Anila already explained the kind of basic characteristics of PV. I'd like to add some before showing the research outcomes. Okay. PV itself is a kind of abbreviation of photovoltaic, and PV can be installed integrated manner. This could be called BIPV, building integrated photovoltaics. But this project is a PV placed on top of the existing properties, so kind of retrofit. So PV kind of mounted structures. The commercial level PV is kind of modularized, standardized. The modularity of the units provide lots of benefits, obviously. And modularity of units helps facilitate our choices and the designing and the planning. It also helps reduce the kind of lead time for the installation of the PV. And use of the PV definitely lessens exposures to the kind of fluctuations of energy prices and up and down and up and down and getting higher and higher. This tendency is obviously increased over the years to come, unfortunately, but this is a reality. And the PV technology, maybe 10 years ago, was relatively new and kind of eccentric, but nowadays it's readily available, reliable technology, and PV systems doesn't have any motions, moving components or parts. So virtually, it's little and maintenance free. And the PV doesn't give any noise when it comes into operations, which is also one of the features of PV. And the PV obviously doesn't give off any toxic gas or pollutions or CO2. And CO2 is the elements that contribute to global warming. So it is very important to implement the device to tackle issues arising fuel poverties as well as global warming aspects. The solar energy is everywhere, and even here in Scotland, we experience cloudy conditions, but even cloudy days we definitely benefit from the solar energies and gains for lighting and heatings, as well as power generations when PVs is installed. This is the case. And if the PV is well integrated, and BIPV is a well integrated PV, kind of provide bold statements of kind of a green message. And also, to some extent, PV can function as educational tools, influence other people. Okay? It was the creation of low or energy carbon communities, okay? And so on. To operate PV, okay, there are a number of devices must be incorporated in addition to PV panels. Yeah. And this diagram shows some components, most of items, obviously PV panels. Yeah. And PV generates electricity in the form of DC, direct current. Okay. But most of the, electrical appliances usually powered by AC. So DC power needs to be converted into AC. So DC AC conversions can be done through the inverters. And this AC electricity will be distributed to other electrical appliances, lighting, fridge, air conditioners, and so on, through the distribution panel, okay, which is this. Okay. So this is the inverter, PV panels, and distribution panels, and excess of energy generated by PV nowadays can be sold to power companies through the meters. So therefore, net metering is a meter is the another component and needs to be incorporated into PV system. Once again, meters, distribution panels, inverters, and PV panels. These are most of the items for the operation of the PV. And the PV, generated electricity will be run through the wire, okay? And this is converted into AC. Okay? This process eats, certain amount of electricity. Therefore, PV output could be discounted through wiring and also inverters. These deductions needs to be taken into the considerations for further assessment of PV performance. In addition to technical features of PV systems, there are a number of kind of soft aspects, architectural considerations that needs to be discussed. So this section is more focused on this sphere. Okay? Try to understand where the PV system should be located. Okay? Location, 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 obviously. So location factors are very important. Okay? The PV needs to be placed properly. Okay? So properness can be defined by the notions in which the PVs are well lit without being shaded. So the question is where. Okay? And the PV systems should be sized properly and according to required energy energy requirement of buildings and equations. Okay? And the variety of PVs available in the market of today. PVs are standardized and modularized nowadays. Okay? However, there's many products available, and even PV modules are triangular shapes and rectangular shapes, and that opaque, transparent, translucent. Translucent PV is quite fancy, but obviously, efficiency level is not as high as we expect nowadays. But still, it can be applied in the future buildings. Okay? And PV arrays, how the PV panel should be placed, tilt angle, orientation of the panel. These are basics and principles, but we have to take into account seriously. And the external conditions, PV is very sensitive to the fluctuation of the temperature. The higher the temperature, the lower the performance. Therefore, PV systems panels should be well ventilated in order to keep the temperature low. So external conditions, PV array configurations, location factors, these factors are extremely important to identify the location of PV properly. Anila already explained a kind of overview of the project. We investigated 3 properties. And in order to identify the optimal place to achieve a higher level of performance, some sun shading assessment analysis are being conducted. These are three buildings. Left-hand side, this one is a yellow color flat block, a 3-story high, and clad with the tilt roof. And middle building is, and this one is a green building. Configuration is very similar to previous one. And the tilt roof, 45 degrees. The last one is red buildings. So as you can see, roof configuration is slightly more complicated than the other two. So shading assessment has been conducted with due consideration of some positions, because of the some positions are changing all the time throughout the years. Summer sun is different from winter sun in terms of the qualities and availabilities. Qualities may reflect a level of incoming solar radiations, and the availabilities is the time of exposures, completely different in summer and winter. So in-depth analysis had been carried out. Well, this is one of the snapshots of shading patterns of the site. This is the summer conditions. 21st June, obviously summer solstice, in which the sun reached the highest point. So summer solstice. If you take a look at the 3 buildings, the left one is quite obvious, isn't it? Number of chimneys projecting over their rooftop, and chimney, these projections cast a really large amount of shadings. And the middle one is only one chimney placed on top of it, but actually 2 more placed on each side. The last one doesn't have any large chimney projections in the middle of roof, but 2 chimney placed both sides, each side. So this case is rooftop is quite clean. There's no trace of shadows, but it's quite obvious. Building itself is tilted slightly towards southwest direction, so tilting orientations definitely affect the solar performance. Incoming solar radiation level can be reduced as little as maybe 10 degrees, 10% or 15%. So other buildings, 2 buildings is facing due south. So this one, in terms of orientations, these buildings are more optimum as opposed to the right one. And speaking of the distance between the buildings are also critical factors, architecturally speaking. And because this building is also cast a shadow, but the clear distance prevent overcasting, shadow over their buildings. Unlike the situation right there, 2 buildings are put together very closely. And in addition to that, south-facing facade is middle-wise slightly set back, So kind of staggered profile and configurations. And obviously, this kind of arrangement leads to the generation of the shadows. I can show next slides. If you take a look at this portion of a rooftop, left part of the rooftops is well shaded actually. And due to adjacent buildings, this corner casts a shadow over the adjacent buildings. Yeah. And another interesting aspect after this shading analysis was northern part of the rooftop is very dark. So this image tells us that a northern part of rooftop is not really a good place for PV installations when the optimum performance of PV is a concern. So this case is an autumn situation, 21st of September, so meaning this implies the equinox, autumn. The next slide shows winter conditions, and which is 21st of December, winter solstice in which summer, the sunlight reached the lowest levels. So it's level of solar radiations is relatively low, but quite interestingly, if you take a look at this roof, a south-facing rooftop, there's no trace of shadows, so well lit. That's quite interesting. So maybe because of the availability of sunlight is limited, summer sun and winter sun is a different situations. And in summer times, the sun comes behind the building, and the winter sun comes from the front. So this case is the front. Therefore, the rooftop is well lit, right? And now, spring, 21st March, spring situation is very similar to what I saw previously in the autumn situation. So take a look at a corner of the rooftop is shaded, right? Because of this particular configurations. So these three buildings initially investigated. These buildings have their own architectural characteristics that affect the performance of PV. And as I mentioned previously, the lift building is a yellow building, has many chimneys that cast a shadow. And the middle one, which is green building, we call it, one chimney is projecting somewhere around there, but most of the south-facing rooftop is quite clean. And the last one is a red building. Is a rooftop is clean, and there's no object that casts a shadow. However, the building itself is tilted. Therefore, this helps reduce, unfortunately, this helps reduce the solar opportunities at nearly 15%. So according to some shading analysis results, we concluded that this middle one, a green building, it was considered as a building which has a huge potential to generate more electricity throughout the year than in other tools. And therefore, a further in-depth study had to be carried out in order to identify the performance. But before that, we also take a look at more details investigation on the rooftop. I'm going to show a little more. So if you take a look here, it's a little projection. I'm not talking about chimney. I'm talking about now is drainage pipes. Even drainage pipes, south-facing projection, actually generate shadows. Okay? So if the PV is placed around here, okay, these tiny drainage pipes still degrade their PV performance. Okay? Therefore, they are all objects, okay, that may harm PV performance must be well investigated. So once again, this is the green buildings, spring situations, summer situations. Surprisingly, this particular chimney actually serves as an element that casts shadow over the subspacing rooftop. Reason behind it is quite simple. It's a summer sun. Sunrise, sunset occur behind the buildings because it's summer. And unlike winter, this is quite interesting result. In autumn situations, same as through, is the left portion of the buildings well shaded. The winter situations is surprisingly very clean, and no trace of shading on the rooftop. However, a south-facing facade is actually receives shadows. And this image also tells us that south-facing facade is not really a good place for PV installations. When optimal use of optimal performance of PV is concerned. Now, furthermore, we also conducted research hourly shading profile of this particular roof. We want to know exactly when this left part of this roof is shade, starts shaded. 14 hours period of times and solar exposures start from the 5 o'clock a.m. and finish by 7 o'clock p.m. 14 hours. 5 to 6, 6 to 7, 7 to 8. And if you take a look at the buildings closely, in the morning, there's no shadows up until noon. So goes to the next slide. Evening is a really similar situations. Is quite clean, no trace of shadows up until right there, sort of 5 o'clock. So after 5 o'clock, this portion of a particular portion of the rooftop will be shaded, affected by the surrounding object. So this investigation tells us that this particular rooftop in creations has a huge potential for solar exposures during the daytimes, not after 5 o'clock. But it's feasible enough to harvest solar energy shown during, given during the daytimes. And according to shading, sun shading analysis outcomes, central part of the rooftop was considered ideal for the placement of the PV. The central part was selected not only because the sun shading profile, but also kind of more architectural aspect as well. Symmetrical visual balance is also very important to some extent because our PV is very visible. So people walking on the street and they can see it. So architectural kind of integrations is another dimensions of our discussions used as educational tools to influence the other people and neighbors, communities. So this central portion is big enough to accommodate 42 PV panels. So 42 panels are estimated to accommodate 10 kilowatt peak PV systems. and the roof area is 70 square meters. Okay. Another question arose, okay, how can we place the PV, the panels vertically or horizontally? Okay. So in this case is a PV panels placed horizontally, okay, kind of traditional way. Okay. The other option is a PV panels placed vertical. Okay. Try to concentrate, okay, the central part of the roof. But however, as we already saw the situation previously, the distance between chimney and solar panels, the distance between the drainage parts and solar panels are critical. Okay? Because this object has a potential to cast a shadow. According to the investigations, okay, we concluded horizontally extended PV panels should be applied for purpose of this study. So that was our final conclusions. And based on the results of shading assessment or analysis, and a further technical aspect, performance of the PV and cost effectiveness was investigated by Professor Muneer and Edinburgh Napier University teams. So I'm going to pass on to you for further report of a more technical aspect of PV implementations.
Hello and good afternoon to all of you, people in this room and people outside this room. First of all, I'd like to pass my thanks to Dr. Branka Dimitrievich and her team at Kickstart to fund this feasibility study, and also thanks to my colleagues Anila, Ahmad and Dr. Masa Noguchi for leading the project. My work is coming at the tail end of the project, as you will soon see. I'm going to present the technical analysis, and that analysis would not have been carried out if we didn't have the proper specs from the cooperative, housing cooperative, and also the very detailed shading analysis which was carried out under the direction of Masa. So let's make a start on the technical aspects. First of all, in this graph, which doesn't seem to appear in full here, yes, now it is, it shows you, in a way, it is summarizing the prospects of PV despite the serious government cuts that have taken place. As my colleague Anila has mentioned, the government launched this feed-in tariff, which is generally known by the acronym of FIT. FIT was introduced in Germany and Japan about 10 years ago, and they reaped the benefits. So they have a 1 million roof program over in Japan. They had a 100,000 roof program in Germany, which was extended to 1 million roof program. They are leading by a big margin. So to give you a summary, in Germany, they are close to 20 gigawatt installed PV capacity. In UK, it's an order of megawatt at the most. And then the government, because of its commitment to the carbon reduction program, it introduced in April 2011 the feed-in tariff. And within 8 months, by about 8 December, they had decided that they were going to halve the rate from 43.3 to 21 pence per kilowatt hour. As a result, Fairfield had to dramatically reduce their intentions. They had intention to go for a 10 kilowatt, which is the subject of this present study. From 10 kilowatt, they went down to almost 4 kilowatt. So that is the state of affairs. But I believe PV will succeed eventually despite lack of government support, because this graph is telling you. So what we're seeing is from 1984 to now, well, up to 2010, there was an 80% reduction in the open market PV price. But in the past 2 years, the price has further dropped now. So the latest issue of sun and wind energy is quoting a price of 0.86 US dollars. So it's 86 cents per watt peak. Now that's a dramatic cost reduction. So in countries such as USA, Japan, Germany and China and Italy and Spain and Portugal, they have got gigawatt plants now. I hope through this feeble effort we can persuade the policymakers in this country to think again about the feed-in tariff. Certainly, I've raised with the Scottish politicians this issue that we should start production of PV modules here, and if not, we should have subsidized rates within Scotland at least. I've raised it with 1 or 2 ministers in the Scottish government. So this downward trend, if it continues, and as I say, is now gone below $1 for the PV module cost. But remember that there is always a module cost. So the PV module cost is one of the total system cost. So the system cost, you can say, is now running below $3 per watt. But we need further reduction for it to compete with grid electricity. But the time is coming. The Germans are predicting that by 2016, that time will come, that PV electricity will compete head-on with the grid electricity from fossil fuels. Now, as my colleague Masa has mentioned, the shading is a very critical issue in PV design. So what I'm showing you here in this graph is there is the curve of what you expect as the full output from the entire module being 100% sunlit. So if there are 36 cells in a module, that's the curve for 36 fully illuminated cells. But if one cell out of the 36 is shaded, the output will drop to this. Now that's a very serious setback of PV. But the industry is attending to this problem. This problem arises when all the 36 cells are connected in series. So you can imagine if you have a long road, a motorway, let's say, which could be 50 miles long. But if one section of the motorway gets clogged, the entire motorway gets affected. Your journey time will be reduced significantly. So the same is with the PV modules. If one cell is shaded, there is a blockage of the flow of energy, and this will affect the entire module. So the way the manufacturers are attempting to solve this problem is by putting bypass diodes for not the whole module, but for each row of cells or so many cells, they will have bypass diodes. That will increase the module cost, but it will ensure high efficiency even under partial shading conditions. So this issue is very, very critical. So just to amplify that point, this building which I'm showing you, the rooftop of that building, was constructed in London, and they had a good potential for PV output. But then after a while, a building was constructed in the close vicinity. Now this is where again the planning laws should be looked very, very carefully. So as you can see, on that hour, a lot of PV modules are under shade, and that will seriously impair the performance. So all these studies were taken on board when we designed the facility for Fairfield Housing Cooperative. and as my colleague Masa has shown, the site we had chosen was absolutely brilliant. It was shade free almost throughout the year except low winter sun angles, and it would have delivered, but because of the reduction in feed-in tariff facility, the whole 10 kilowatt facility could not be installed. Now I'm going to take you through some technical details. How does one attempt to take a design of PV system in place? As Masa mentioned, the external conditions are very, very important. For the given location, you've got to have as accurate data for solar irradiation, which is available on that site. Usually the meteorological office measures these data, but on a horizontal surface. And again, they will only measure in most locations the total energy coming from the sun and the sky. So there is a split. How much energy do you get from the sun? How much energy do you get from the sky? The sky energy is known as diffuse irradiation, and the sun's energy is known as beam irradiation. The sum of the two in the scientific community is called global irradiation. So if you go to Met Office website, there are something around 70 locations in UK where they can provide you measured data, hour by hour measured data for global radiation throughout the year. But some locations such as Perth, they are not in that list of 70 locations. So how do you go about it? Well, you have other sources. NASA, for example, they have measured through satellites detailed data sets they have for all parts of the world. So you go to the NASA website, you key in the latitude and longitude, and you will get for that particular location the monthly averaged data for the entire year. So you'll get for January one figure of global radiation. February you'll get likewise. But that's the total radiation, the global radiation on a horizontal surface per day, which is the average for that month. So what you need to do is, from the shading analysis, you know which day, which hours of which month are under shade, the facility and so on. You need to break up the global radiation per day, first of all, into the two components, the beam radiation and the diffuse radiation. You do that first. And then you split the daily values into hourly values. That's done through very well known and proven statistical techniques. And that's what is shown in this algorithm or flow diagram here. So you take the location details, the latitude, longitude, you take the position details. For example, for Fairfield, the site we have identified, it was nearly south. The building was facing nearly south, and the tilt angle was known, the slope angle for the roof where the panels were sitting. You feed in all that data into the software which we have built at Napier University, and then you will be able to get how much energy you will get on the modules hour by hour. And that's what we have done for this project. Then if you follow the steps from there on, that's your slope irradiation, I call it. So that's hourly values of how much energy coming from the sun and the sky. Next, you find out when the module is being hit by this much energy and the air temperature is so much. Obviously in Perth, the ambient temperature will not be high, which helps the module efficiency. The cooler the module, the better the performance. Nevertheless, the cell which will be laminated behind a glass sheet, it will get hot and its temperature will rise above the design temperature. So the manufacturer of the PV module will report to you the efficiency at 25 Celsius module temperature. In most cases, the temperature of the module will exceed that because of this warming. It's like a greenhouse effect. You got energy going through the glass, heating the cells. So you have to find out how much is the cell temperature, because then you'll use the manufacturer supplied data to find out what will be the efficiency under those conditions of so much ambient temperature, so much intensity of solar irradiance. So then you will be able to find out the module characteristics, and then you will be able to find out the power output. How much would, so we had chosen for this study a German manufacturer, Scott's 240 watt peak modules, but you may find under say summer condition it drops to maybe 200 watt. So you can find this hour by hour for all the months. Okay, so that's the flow diagram. We've gone through that, and here is now the results emerging from the modeling and simulation exercise. So what we were proposing was the spec given to us, the design team, was the Cooperative wanted to go for 10 kilowatt peak. So we were of the opinion to go for 42 Scott panels, each of 240 peak power, and for those 42 which were to be arranged in 3 different strings. The string is a connection of the modules. So if you recall, my colleague has shown you the horizontal layout as being the optimum layout. So we were going to arrange them in 3 strings, each string connected to one inverter. The more the number of inverters, the better it is, because if one string is under partial shade, the other string will not be affected. If you have one single inverter connected to the entire 42 panels in series, one panel in shade, the entire string would go down in performance. So we were proposing 3 inverters. So this is the monthly output for that design which we are proposing. Now, one question which was addressed in the report was the environmental impact of the panels. So a number of people at least used to believe that the panels have are so much energy intensive that in its production or in their production, the energy which goes into in the form of embodied energy is never paid back. I installed a 15 kilowatt facility at Napier University back in April 2005. And for 3 years it was under very detailed scrutiny as part of a PhD program. So we had already found with that facility, which was not on the optimum angle because it was a retrofit application, so it was in a vertical wall. Whereas for Fairfield, the angle was very close to the optimum, which should be 45-degree tilt angle. The rule of thumb is, if you face your panels in the northern hemisphere towards south, and you have the slope of the panel, or tilt as it is called, at 0.9 times latitude, that will give you the maximum energy output. And this rule have been checked by University of Wisconsin and us at Napier and so many other places, and it is a very valid rule. So it's not just rule of thumb, it is a validated rule of thumb. So for Edinburgh or Perth, which are at a latitude about 56 or 56.5 degrees north, the optimum tilt would be 45 degrees. Whereas at Napier, the panels were tilted 75-degree angle because it was a retrofit. Even under those non-optimum conditions, we found the panels would pay back 3 times over in their lifetime. The energy output would be 3 times higher than embodied energy. But what this slide is telling you is, we are looking at a wider picture here. So this slide is saying that in southern European climes, the embodied energy will pay back within 1.2 and 1.8 years. And the average reported by European Photovoltaic Industry Association is 1.5 years, where the radiation level is 1400 kilowatt hour per meter square. For Perth, we found the daily radiation average over the whole year was about 2.5 kilowatt hour per meter square. So if you multiply 2.5 with 365, it will be lower than that 1400, which is for Central Europe, but still not very far away as people think. However, if you go to countries like Saudi Arabia with a radiation income of 2000 kilowatt hour per meter square, the payback period is under 1 year. Under 1 year, the panels will pay back. And the life quoted for the panel is typically between 20 and 25 years. So for roughly about 22, 23 years, they're delivering really free, carbon-free energy. So that's very important to know. So as part of that report, what we have done is we have addressed 3 issues which in my philosophy are very important for any engineering project, not just PV. You have to look at 3 E's. The economy, which is the monetary payback. Because economy can be misleading figure. Economy doesn't just mean money. Economy could be energy economy, carbon economy, and so many things. So I'll always say in full, economy meaning monetary economics. That's 1 E. The other E is energy. I just gave you figures for embodied energy and how long it could take to pay back, or how many times over in its lifetime it will pay back. So that's the 2nd E. And the 3rd E is environment. That is the carbon economy. So in this report, we have looked at all the 3 E's. So we've shown what will be the carbon payback, what would be the monetary payback, and we came up to the figure of 7 years if the panels are kept in pristine conditions, or 10 years if they are left to the vagaries of the sun and rain and hail and so on. Because the dust cover is a realistic thing. It will happen, and there will be degradation of the performance because of dust buildup, bird droppings, and so on and so forth. And this is only obtained by practical experience. You cannot model these things easily. Because I have operated a facility of 50 kilowatt at Napier for past 7 years, I know the degradation will take place. So just to give you a figure, at Napier University, the panels were BP Saturn panels produced in Spain. The quoted figure was 17%, but in reality, they will change month by month, but the variation was between 11 to 14%, the measured efficiency, because that takes into account the dust and dirt buildup, the bird droppings, the inverter losses, the cable losses, and so on and so forth. So based on that, I would say that the payback for Fairfield would have been 10 years, not 7 years. But still, it would have paid back 2.5 times over in a life of 25 years. So in the report, there is great detail of all these measures, which I'm showing you. One such sample is there. That's the meteorological data obtained from the NASA website. And the PVGIS software, for example, it let you link directly with this database. It will cover the entire globe. So those are interesting figures there. We also provide hourly performance of the voltage delivered, the current produced by the modules, the power produced by the inverter, the cell temperature. All those details are part of the modeling output. So this is for the remainder 6. For the first slide was the first 6 months, this is the next 6 months. And this slide is showing you the monetary payback year upon year, and the column is shown in red is the 7th year. So if, as I say, you're really going to go on the roof and clean every day all the modules, you will get it payback in 7 years. But more realistically, 10 years. Now I'm coming towards the closure of my presentation. And again, I'm coming back to the point that we need a serious policy shift towards renewables. And this is one such figure. It shows you the installation which are going on at a rapid pace, despite all the recession and everything, in 4 European countries. Germany, as you can see, is the leader, followed by Italy, and then Spain and France. They have gone to gigawatt capacities, and in UK, we are in wind. UK is doing quite all right, especially Scotland. Very ambitious plans, and also good action has been taken place. But on PV, we are a bit behind. We're dragging. So another message: at the end of 2011, Germany had installed 29.3 gigawatt capacity of wind and 25 gigawatt solar power. The Sun and Wind Energy magazine reported that in 2011, on a summer day, the PV electricity in Germany was 31% of the country's intake. 1/3 of the energy was produced by PV on a sunny day. That's very, very big figure. Regarding the cost, I've already mentioned the Chinese average crystalline silicon module price fell to $0.96 per watt in January 2012, and a low price of $0.96 per watt was recorded for large orders from German distributors. So these are the latest issues of renewable energy world. Just to give an outlook on what actions are taking place in the industrial sector, here we have a newer kind of technology, heterojunction modules produced by Sanyo, and they will hold the efficiency at higher temperatures as opposed to the classical technology, just crystalline silicon. The HIT will use a sandwiched design of amorphous silicon and crystalline silicon, and they therefore maintain the efficiency at a higher level even under higher cell temperatures. So all these actions are helping bring the price of the delivered wattage as low as possible. So that's the end of my presentation. Thank you very much. And we can now take questions.
Thank you very much, Tariq. Please take a seat over there. Thank you to our speakers, and now we can start with our questions and answers session. We have already a few questions from our online viewers. So let's see. The first question is from Marisa Castillo of Team Planners. Would it mean that the design of solar PV systems cannot supply the needs of an ordinary family in a house? Who would like to answer that? That was related probably to the start of the presentation. So could you say whether a PV system can supply energy for the needs of one ordinary family?
Well, well, I think it's always between the balance between housing energy needs and housing, the energy supplies. So I'm not really clear about exact questions. However, it depends on the capacity of PV. So how big the PV, systems have been chosen, and if the ordinary house, the capacity is a conventional house is for example, is 20,000 kilowatt hours of energy required. But if you have the 4 kilowatt system of PV is implemented, is this generate electricity is not completely a package of the energy demand. So it's always there's a balance between the two. So PV system should be, as I mentioned previously, a PV system should be the size of the PV system should be determined and well assessed in consideration of the the energy requirement. So without identification of clear energy requirements, it's very difficult to answer. PV cannot supply all, but in reality, it is.
I see that Marisa Castillo has also added. Thank you. I think that the last speaker was already answered my question, so she's satisfied with the information that she received. A question from David Whitelaw, Green Energy Advice Ltd. What software was used to simulate the shading, and where can I get it?
Well, this shading analysis had been conducted using Ecotect, is the one of the software readily available in market, and which is the sold by Autodesk. I used to be a Solar One, but now it's Autodesk. But in order to carry out shading analysis, a very important thing is to visit the site and understand the site conditions and document it using pictures or a photograph. And then based on the photographs and site visit, and then modeling should be carried out. So the software itself is called Ecotech.
Ecotech. And where can it be bought?
It can be bought through anywhere, internet. Autodesk is the company Autodesk is the company which market Ecotech today.
We have a question here in the audience. Please introduce yourself and ask the question.
Hi, Ewan Barr from Tenants First Housing Cooperative. I wanted to ask Anila, do you have maintenance plans for the panels that you've put up? Because I thought it was important. It was interesting that Tariq was saying that the maintenance to ensure you get the quickest payback was very important.
Okay. Good question, that. The panels that we eventually went ahead with and put on the office, they're actually self-cleaning panels. So when we had a chat with the PV installer, they did say we wouldn't have any need for a maintenance or a cleaning contract. So that's something we haven't bought yet, but something perhaps we'll look into going forward, so perhaps maybe in 5 years' time, 3 years' time. But at the point of purchase, it was mentioned to us that the panels themselves are self-cleaning, so there's no need to purchase another contract, whether it's through them or someone else, to clean the panels.
Thanks. There was just one other point that for Masa. I know that the original building that you said was optimum was the south-facing one, I think, from your presentation. But you ended up going for the office, which is a southwest orientation, and the 45-degree angle, I think, is optimum on the roof. But you've got southwest. Could you have used? I see there was a flat-roofed extension. Could you not have considered having them on the flat roof and orientated south?
It's quite good observation, actually. It's speaking of architectural conservations and installation of PV, as I showed a couple of slides previously. There's clear parameters, and the tilt angles and orientations are really critical. And if compare between the two, already tilted, sloped roof and flat roof. Flat roof is there obviously provide kind of flexibilities in terms of orientations of the panels and the tilt angles, as opposed to the tilt sloped roof. Because of the sloped roof, retrofit is a location factor, is a constraint.
Repeat the question. Regarding the 25-year life, what are end-of-life options for photovoltaics? Can they be recycled in any way?
First of all, the modules are silicon-based, so they're not poisonous as such. And then the local councils, they would have in place measures of safe disposal of these panels, like anything else they have. So any person who is approaching the end of life of the panel, they should consult their local councils, and they would be able to get good advice.
Thank you very much.
And also, I'd like to add some comments. One of the Japanese research institute actually investigated PV modules used after 40 years. And it was quite interesting research outcomes. There was the PV cell itself is still useful. However, some peripheral, the parts and components, the packaging, the glass, and these kind of things needs to be replaced. And PV cells is usually sandwiched, tempered glass, and also some other aluminum frames. These components are obviously recyclable components, but the PV cell itself can last quite long. That was what they found.
Thank you very much. A question from Ahmad of Robert Gordon University. Some shaded PV panels can still produce some energy if they use the diffused light. Will a module where few panels are in this situation still suffer from the problem you raised, or your observation concern the old technology that works only with direct solar radiation?
The panels will work in any light. I never said that they will only work with direct solar radiation. But what will happen is, if there is shading, no matter what conditions, diffuse or direct sunlight, there would be problems. Known as local hotspots will be created where there is restricted flow due to shading. That is the problem, and that should be avoided by not having shading or having multiple inverters.
Mm-hmm. A question from Robert Burzanski, University of Reading. In your payback period calculations, did you take into account costs of technical maintenance? I mean costs of monitoring performance, costs of repairs of faults, for example, inverter after warranty period, and possibly faults of panels.
Yes, we have, because at Napier University we have not a theoretical experience, we have live experience. And I can let you know now that in the 7 years, there was one fuse blown, which cost nothing, because we have a box of fuses supplied by the installer. The panels are just as my colleague Masa said, there are no moving parts. So there's little that can go wrong. At the end of this 25 years, what can happen is the bus bars which provide contact between the cells, they have some material migration taking place. So they get thinner and thinner, and they may break off. This will happen with aging process or vandalism. So if you make sure you're vandal proof, you put in a high place and well looked after installation, there is little that can go wrong. The inverter may have a life of 10 to 15 years, but inverter is a small part of the cost. The big chunk of the cost is the module cost.
Thank you very much. Let's go back to more questions from Marisa Castillo of Team Planners. She clarified what she really wanted to know. My question pertains to an area where there is no commercial power supply. So maybe 230 kilowatt hour per month per family. Can this solar PV supply that amount considering all the needed characteristics of the site and building design are met?
See, as my colleague said, the location, he said. Yeah. So if you are in Saudi Arabia, as I was showing you, you'll get 2,000 kilowatt hour per meter square. You can multiply by roughly 15% or 12%.
What about United Kingdom?
In United Kingdom, in Perth, it was 2.5 kilowatt hour per meter square per day. So you will get roughly, 1/10 of that output as electricity. You follow? So you have to see, if you're living in a flat, which you have one roof shared by say 3 flats, then the area is not large enough. You follow me?
What about an individual house which is off-grid? That's what she's asking.
Then I don't know the footprint of the house. If their house has large enough roof, which can be completely covered with the panels, then it might, a typical house, I would have hoped, would get something of the order of 4 kilowatt peak need, no more than that. And if you have large enough roof, you can meet that, but just barely.
Just to add to Professor Muneer's comments, you also have to couple your solar panels with lifestyle changes. So obviously it does depend on things like, how big the roof is, how big the system is. But if you want to satisfy all of your energy needs through not using the grid, just using the panels, then you will have to make some lifestyle changes. So for example, the big energy consumers like your washing machine, your dryer, that kind of thing, use those at daytime. So for UK residents, most of us go out to work during the daytime, so we don't use the kettle during the daytime, we don't use the dryer, the washing machine, that kind of thing at daytime. The advice that we got from local PV companies was the tenants will have to make lifestyle changes, like perhaps set up a timer to use the dryer, washing machine, other items during the daytime. So I suppose that you can satisfy the majority, if not all, the energy needs, but it'll be a case of manufacturers being taken into account, like you said, the size of the system, the size of the roof, so on and so forth, but also lifestyle changes will be a big element of that as well.
I think that's very true. Yeah, it's heavily rely on implementation of PV alone is quite dangerous. So it's energy consumption is obviously related to user behaviors and how the house is actually used. So maybe it's really very important to start with the try to reduce the energy requirement of the house. And according to my rough calculations, 1 kilowatt system, peak systems here in the UK, it can generate roughly 700 kilowatt hours per annum. So, and in this case, is 230 kilowatt hours of energy requirement per year. So just multiply by 12 months is going to be 2,760. So this amount can be covered by, if PV alone, 8 kilowatt peak of PV panels, if installed properly, it may be cover the entire energy demands. Yeah.
Thank you very much. A question from Marsha Smith, Sustainable Matters. What is your opinion on microinverters, 1 inverter per panel, with regards to their performance under shading conditions?
Sorry, would you repeat that, please?
What is your opinion on microinverters,
Yeah.
1 inverter per panel, with regards to their performance under shading conditions?
So that would be an excellent thing to have. And I know there's certainly a US manufacturer had plans to bring on the market by this year, and the Sun and Wind Energy actually carried a picture of that panel. That single panel had a built-in inverter at the back of the panel, and it would produce 1 kilowatt. The height was taller than the chief executive who was holding that panel. It was in the issue, one issue of the sun and wind energy. And that company had plans to bring that into market. One inverter per panel. So you have a panel which gives DC, AC output direct, and 1 kilowatt of it under peak conditions. Now that is the way technology is moving. So if we have that kind of technology, yes, fantastic.
However, I think in terms of the price is obviously more expensive than lower number of inverters. And the shading is one of the key aspects of PV installation. So each panel has their inverter, so it also avoids shading negative effects. But on the other hand, inverters eat to some extent electricity, so efficiency is not as much as centralized inverter systems. But there's always kind of balance that needs to be taken into account, I guess.
Okay, a question from Sarah Gaunt of National Energy Foundation. Did you calculate the potential impact of photovoltaics on levels of fuel poverty or other social impacts within the housing?
Yeah, it's a very, very good question. But our study was focused on the design for the Fairfield housing community. The energy cooperative, as you know, is a very intense topic. The sociologists are very much interested in that. So it's a topic of great debate and discussion, and I wish if I had a grant, I would love to engage myself and my students in that, but that's a different topic altogether. No, we did not go into that area.
A question from Douglas Bly of Queen's University Belfast. Would you recommend that an expensive solar package be purchased with high energy efficiency instead of buying an average efficiency package with a lower price tag in relation to payback over the product's life cycle?
Well, one should sit down and do the sums. That is the answer. Talking qualitatively will not give us the right answer. They have to sit down and do the sums. This is the capital cost of this. This will be the maintenance cost of it. And this is my per kilowatt hour over the 25-year life. And then you do with the option 2. And then you'll come to the answer. It is not possible to say go this way or that way until you do the sums.
And also, there must be a kind of opportunities to use use the heat from the PV as well. Well, this is slightly outside the scope because of the PV itself generate large amount of heat, energy, thermal energy. So if you choose the lower efficient PV, more coverage required. If you choose the high efficient PV, PV coverage becomes shorter. But speaking of the thermal output, lower efficient, cheaper PV can actually generate more heat. So this heat is can be supplement space heating if integrated properly or intellectually.
Well, I think we are now close to 2 o'clock, and there are a few more questions, but we will ask our speakers to reply to these questions by email. I would like to thank to our speakers and to our audience here and online, and just to draw attention to our forthcoming events. First of all, we are planning a live conference entitled Micro-Renewables for Buildings and Transport, Deliverables and Barriers. This will be a conference to be held at Edinburgh Napier University on 18th of April. The keynote speaker will be Professor Jeff Livermore of the University of Manchester, a lead author on the 4th report of the International Panel on Climate Change, who contributed as a member of this panel to the award of the Nobel Peace Prize in 2007. There will also be 14 other speakers from universities and companies who will provide useful insights to current and possible future states of play in micro-renewables for buildings and transport. Mitsubishi will be showing off one of their electric cars. There will be no live stream from this conference. It will not be transmitted online. And if you wish to attend, you can register to attend in person on our website. So please access www.cicstart.org to see the conference program and book your place. Then we will have a webinar on Thursday, 19th of April, entitled Benefits and Options for the Retrofit of an 18th Century Traditional Scottish House using the Passive House Standard. This is a study undertaken by Edinburgh Napier University and SA Estates. So we look forward to welcoming you at our forthcoming events, and we would like to thank you for watching the webinar today. Thank you very much.